Bismillahirrahmanirrahim. Okay, we were talking about the resolution of a DT signal into impulses. So we'll start with this. Before starting to this, if you have any question from the last session. Okay, so today our main focus is to discuss about the convolution and how the convolution actually represents the output of a system when we know the impulse response and inputs for arbitrary inputs. So that is the main concern of today's lecture, and apart from that, there are some other few issues we'll discuss, inshallah. So if we concentrate on this title, the resolution of the DT signals into impulses, how the impulses can be incorporated with your input signal to represent the output of the total system. So step by step, this is the xn. This is an arbitrary inputs. We have the inputs for the zeroth sample, -1, 1, 2, 3, 4, 5, 6. For the different positions, we have different values. So if we concentrate on the point of xk, where k is 4, so it's like x4, it means that this is a constant. For an arbitrary input, this x4 contains some value. Let's say the value is 1.5. So if I mention that 1.5, it doesn't mean anything. Rather, it shows only the value. For the discrete time signals, we need to also represent the location. For that one, what we can do, we can multiply this value with the delta function shifted for 4 samples. So n minus 4. As we know that the value of the delta function is 1 multiplied with 1.5, that eventually give you 1.5. But what about the location? By this function, by seeing this function, we can understand that what is the location of that value. And from there, we can find that there is a 4 samples delayed. So that means if we want to target this sample, we can multiply our xn with a delta function of k value shifted, where k is equals to 4, and then multiply these 2 samples. So we can multiply these 2. One is xn and multiplied with delta function. So that means we can multiply our xn with a delta function n minus 4. That means we only target the sample at the location of position of 4. So what would be the output? Of course, the output would be looks like this. That means we only got the sample at the location of k, or k is equals to 4. If we want to take only the sample at the 0th location, then what will be the equation? The equation will be like x0 multiplied with delta n. For the first location, x1 multiplied with delta n minus 1. For the second location, x2 delta n minus 2. Very simple. x3 delta n minus 3. x4 delta n minus 4. Try to understand that for all the cases, this first value actually represents a number which is constant for a particular input value, a series of input of xn. The second one is a delta function and the shifted version of the delta function, just to mention the position of the signal. So these are the multiplications. which actually gives you the same value as x0, x1, x2, x3, and x4. And also it also mentioned the position of that signal. After that, of course, there are other samples before and after. If you add all those things together, it actually represents what? It represents the whole signal of xn. So xn is equals to, we can write x0 delta n plus x1 delta n minus 1 plus x2 delta n minus 2, and so on and so forth. So by this concept, we can easily mention that our xn can be represented like this. The summation k is from minus infinity to plus infinity. That means that x minus 0 to x0 to x plus 0, and it always multiplied with the sample position delta n minus k. Elaborately, we can give the example like this. Let's say f x minus 1 delta n minus minus 1 is plus 1 plus x0 delta n plus x1 delta n minus 1, and so on and so forth. That is nothing but our input xn. So we have established that any arbitrary input can be represented by the input signals, values, and the impulses. Impulses means the delta signal or impulse signals for different positions, shifted version of that. Okay, so in future we need this concept to represent the convolution sum. Please go through this example. Whenever I'm mentioning some example, please don't forget to go through that from the book. Okay, this is very important to make your concept more concrete and clear. Response of LTI system to arbitrary inputs. Response means this is the output. Output is also mentioned as a response. So that is known as the convolution sum. So today we'll try to give you the explanation for the convolution sum, and that is for the LTI system. Convolution only can be done for the LTI system. That means for the linear time invariant system. For a nonlinear or non-time variant, that means nonlinear or time variant system, the convolution sum cannot be performed to find the response of the system. Okay, let's think that our system is an arbitrary system. It is not an LTI system. So step by step, we'll mention where to fix the LTI system, where to think that this is an LTI system, and where is not. For a convolution sum, okay, we already know that, we have already proven this. The xn for any arbitrary input, we can represent our input like this in the previous section. Now, for any arbitrary system, we can represent our output like this, where xn can be represented like this. Now, inside the system, we have two components. One is the constant xk, where k is from minus infinity to plus infinity. Another one is the impulse, where the impulse is shifted. Now, we can say that our inputs are the combination of the constant value. Those are the constant coefficient. Try to understand that the xk is the constant coefficient. Those, for example, x minus 1, let's say it is 0.5. x0, that is 1. x1, that is minus 1. So some sort of this. So those are the constants and the constant coefficients. So that's why if and only if this system, the tau, the system is a linear one, then what we can do, we can take these xk's out of the system. And then only the impulses are inside the system. So we can take our input outside the system because this is a linear system. Let this is a linear system. If that is a linear system, then we can write it. From this equation, we can write this if and only if this is a linear system. Now, from our previous concept, we can write it like this. This is a constant part. We can have that, and after that, it is multiplied with hn comma k. What does it mean? Hn comma k. What is hn? Of course, that is an impulse response. And hn comma k means, from the previous lecture, we have understood that if your delta function is given to the system and you are getting the impulse response, then if we shift this value first input and give it to the same system, this output is known as hn comma k. We do not know still whether this is a time variant or time invariant system. So directly, whether this is a time variant or invariant system, we can write it directly. That means the impulses, what is the output of the impulses is called the impulse response, and it can be mentioned as hn comma k. At this moment, we thought that the system could be time variant or time invariant, any of those. Now, if the system is time variant, invariant, then what we can write, of course, we have this. And if the system is time invariant, in that case, after shifting your input, give it to the system, it will also give the same output as the impulse is shifted for k samples, and that is equals to n minus k. According to the properties of the time invariance, we know that if hn comma k is equals to hn minus k, in that case, this is a time variant system, a time invariant system. So if this is equal, then we can write the equation like this. Previously, we have written here hn comma k because we don't know that whether this is a time variant or invariant. Let that the system is time invariant. In that case, we can cancel out this and we can replace it by hn minus k. Now we can say that this response equation is for both linear and time invariant system, LTI systems. And this equation is nothing but the convolution sum. We need to examine this equation definitely with some example, but this is known as the convolution sum. What is the significance of this convolution sum? The most important significance of this convolution sum is that if we know the impulse response of a system, that means Hn, for any arbitrary input Xn, any arbitrary input, you do not need to know what is your input. If we know only the impulse response of your system Hn, for any arbitrary input Xn, we can find the response of Yn. You do not need the physical system. If you just know the impulse response, then by mathematical calculation or graphical representation, you can find the output. This is the most important perspective of the convolution sum. Of course, we need to remember that this is only for the LTI system. For the other system, you can do this convolution to find the response of the system. So need to remember this whole equation. Just for understanding the first part, you'll see that this is independent. The xk, this part is independent to the response, and that should be because you need all the inputs. You need all the inputs to find out the response. On the other hand, the impulses are the location of the impulses, not actually the impulse. The location of the impulse is related to the response of your system, and that should be. I'll give some example with the graphical representation. I believe that that will make your life easy to understand. So that is the whole equation. We have two parts. One is the input constants, and another one is the impulses, impulse response. We need 4 things to do to perform this convolution. If I write the equation again here, Yn is equals to k is from minus infinity to plus infinity, xk, that means a whole bunch of input, and Hn minus k. So where this folding operation actually started, because when we are trying to find y0, then k is from minus infinity to plus infinity, xk, we need all the inputs, and the h is equals to minus k, which represent that this is a folding operation. So you need a folding operation. Then we need the shifting operation. If we consider y1 or y2, in that case, we need h1 minus k or h2 minus k, which is nothing but the folding operation. So first we need, shifting operation. First we need the folding operation, and this is the folding operation. And after doing the folding operation for the 0th sample, for the first sample, second sample, or y minus 1, y minus 2, for all the cases, we need the shifting operation. And after doing those 2 operations, then we need the multiplications between these 2. And after that, we need to make the summation for all the terms, and then we can perform the convolution. Those are the 4 steps: folding, then shifting, multiplications, and the summation. If we compare the correlation with the convolutions, in case of correlations, we do not need the folding operations. We do not need folding operation for the correlations, because in case of correlations, you have a signal, maybe you have another signal, you need to do the correlations. Just one signal should be stay still, and the another signal should be shifted both in the left side and the right side to minus infinity to plus infinity, and then performing both multiplications and the summation for the sample from minus infinity to plus infinity. So that is the basic difference between the convolution and the correlations. In many cases, people are eager to ask you this question: what is the difference between the convolutions and the correlations? So if you know the process very well, it's very easy to answer. Okay. Okay, so conventionally, we can write this equation like this, where input is here and this is its impulse response, shifted version. Now it can be written in different way as well. Let m is equals to n minus k. So here, from where we can write k is equals to n minus m. By putting those value, we can write in this way. And since you can understand that the m is a dummy constant means any value. M can be p, m can be z, any value. So there is no particular meaning of m. So that is a dummy constant. The value of the m is from minus infinity to plus infinity. That sort of constant. So then m can be replaced with any other value like k. So here we let that again m is equals to k, where m and k both are the dummy constant. So then it can be shown here. It can be also written like this: n, the input is now n minus k and h k. It means that your impulse can be stand still, and your input should be folded first and then shifted in any other direction. What does it mean? Practically, try to understand this. If you have the impulses, let's say impulse response looks like this. Okay, this is your system. This is your system and this is your Hn. Practically, when you have performed something practically, and very practically, if I have the input like this, let's say this is our Xn, input is this 1, 2, and 1. This is 0th sample, 1, 2. Let me ask you, which sample actually move into the system first? Which sample? X0 or X1 or X2? Which sample actually moves to the input first?
0.
Yeah, so X0. That means the X0 will hit your system first. Then which value will hit the input? X1, of course, and then X2. So that's why it is logical that the X1, the Xn should be folded first. If we fold it 1, 2, and 1, fold it at the location 0, -1, and -2. So it looks very practical. So let me draw it again. So you have the system, you have your Hn, you know that, probably you know that what is the Hn, it should be given. And when Xn is hitting to your system, it is basically a folded version from the conceptual point of view. That's why this folding is necessary. On the other hand, you can think in a way, you have your input and your impulse is folded and hit to the input and give the output. Okay, so in both cases, this will represented by this equation, and this concept is represented by this equation. K is equals to from -infinity plus infinity xk. It means that all the value of x and then Hn minus k. That means the impulse will be folded and shifted and make the interaction with your inputs. And this is the block diagram for this equation. And this is the block diagram for this equation. Okay. I'll give more examples. So please go through these examples. They have shown the convolution or how to find the response of linear time invariant system by graphical representation and mathematical calculation. So I have taken this example to illustrate the convolution. So 2.3.2. It has been given that the impulse response of a linear time invariant system is this. So it is given. So it's mentioned that the zeroth sample value is 2, 1 at the first location, -1 is the second location, and 1 at the -1. So we can draw it very easily and determine the response of the system to the input signal. So this input signal is given. So Hn is given and Xn is given. Our target is to find Yn. How to find that? Of course, we'll do the Xn, make the convolution of Hn. This is the equation for the convolution, and the illustrated version is again k is from -infinity to +infinity. Do not memorize this. Try to understand what you are writing. Hn minus k. Okay. So I have taken it from the book for visualization. I'm just amplifying this. Hopefully you can see that, though this is probably a bit blurred, so you can follow the book. Okay. The xk, that is k is a dummy constant, as you know that it can be replaced by the n or whatever the things. So this is our input impulse response. So where the values are given, this is 2, this is probably this is 1, this is -1, and this is 1. And this is our input, and the values are given like this. This is 1, this is 2, this is 3, and this is 1. Okay, what is the first step? The first step is to fold your impulse. So it has folded. Of course, you know that how to do the folding operation. After folding, so what we are targeting y0. What should be the value of y0? As you know that y0 is equals to what? K is from -infinity to +infinity, x k, and h n is equals to 0, so that is a -k. So the folded version multiplying with xk. So this is the folded version, and that should be multiplied with your xk. Multiplication means point-to-point multiplication. So we can perform it. So at the location of -2, we have some value here, but at this point there is no value. So what should be the result? The result should be 0. So at the -1 location, the amplitude is 1. At -1 location, there is 0. That's why this is 0. At 0 location, it is 2. And here at the 0 location, that is 1. That's why the amplitude is 2. So we are multiplying each point to the other point. So at the first location, 1, the value is 2 here in the input, and in the impulse, that is 1. So 2 into 1 is equals to 2. For any other value, as you can see that the folded version of the impulse got all the zeros. That's why everything will gives 0 in the output. So after multiplying, we got this result. So that means we got what? We got only 2 values. One is 2 and another one is 2. So we make the summation, and that is equals to 4. Where this 4 should stand, this 4, we are writing yn. Where this 4 should stand, at the location of 0, this 4 should stand. So this is the value 4. Similarly, we need to find what is the value at the location of 1. If we want to find that, what is the equation? Y1 is equals to summation k is from minus infinity to plus infinity xk, and then multiplied with h. N is now 1 minus k. In which direction it should be shifted? Can you tell me? So we have the folded version. Now this is h minus k. If I have h 1 minus k, in which direction it will shift it?
To the right.
To the right. So you can do the calculation, but you can also remember that conventionally when we are writing hn minus 1, it is shifted to the right. When it is a folded version, that means h minus n minus 1, this is actually shifted to the left because this is a folded version. Similarly, if we write h minus 1, sorry, minus n, that is folded version, and plus 1, conventionally it is shifted to the left, but for the folding operation, it is shifted to the right. So you are absolutely correct. It will be shifted to the right. So whenever you are shifting it to the right, the whole consequence, you need to follow the same consequence. So this is actually folded version, and then we are shifting one sample to the right, and we have found this. And again, we need to multiply each and every sample with your input, with the inputs. We need to multiply those things. And after multiplications, we got this result. For the 0th sample, this is the value. For the first sample, we have this value. For the second sample, we have this value. After adding all those, this is for the location of 1, for the first location. After adding all those values, you'll find that that value is equals to 8. You'll find that the value is equals to 8. So similarly, you can perform perform for all the positions, starting from y0 to y what, and to which value of y. So what should be the range of this value? So from this equation, we can find it very easily. The lower value, we need to summarize the lower value of hn and xn. What is the lower value of hn? It is my lower value, not actually the value, the location minus 1. And what is the lowest value of xn? The lowest location, this is 0. So we can add those together, that is minus 1. So our response will start with the values from y minus 1. And what should be the maximum location of the response? That is again, what is the maximum location of hn? It is 2. And what is the maximum location here? That is 3. So you need to add those together, that is 5. So y5. So it will start with y minus 1 and up to y plus 5. So you can find y minus 1, what should be the value, y0, same process, y1 and up to y5. And after that, if you want to proceed after that, y6 or y minus 2, you will always get 0. Of course, you will get some value, but it will give you 0. And at the end, we have got this result. And as you can see that the lowest value location is minus 1 and the highest value location is plus 5. And this is the result. If you can remember this just for today's class, 1, then 4, 8, 8, 3, -2, and -1. This is the value. In which concept we have done this? By following this equation, the conventional equation x k h n minus k. I'm writing this for several times just to make you understand what we are actually following. So graphically, we are actually representing this. You can also follow the tabular format or the mathematical concept, or by the equation. You can also get the result. What does it mean by having the equation? Let me give one example. Let's say I would like to find y0. This is equals to k is from -infinity to +infinity, xk, h n minus k, n is equals to 0, so minus k. Now it can be elaborated like this. You have the value where you have the, what should be the what is the range of k for the input? It is from the 0 to 3 is the input. Let's say x0, so that means k is equals to 0, then h0. Thus, if we target x1, then h minus 1, plus x2, h minus 2, plus x3, h minus 3. Do you need to proceed more? No, because you do not have any input over there. If you want to find like x minus 1, h plus 1, doesn't mean anything because you do not have any input. So that's why we can neglect those part. And now if I want to put those value for this equation, what will be that? What is the value of x0? x0 is equals to 1 multiplied with h0. h0 is equals to 2, plus what is the value of x1? That is 2 multiplied with h minus 1. h minus 1 is equals to 1, plus x2. x2 is equals to 3 multiplied with h minus 2. Minus 2 is 0. There is no value. Plus x3. x3 is equals to 1, and h minus 3 is 0. So it will also give 2 plus 1 is equals 2 into 1 is equals to 2, plus 2 into 1 is equals to 2, plus 0 plus 0. It will also give you 4. So as we already mentioned that the result at the location of y0 is equals to 4. You can also find it like this. But the main thing is whether you understood the process or not. This is very important. Okay. So I have given you the example, the same example in two ways. One is a graphical representation by considering the equation. Second one is just to putting those values. Okay. Number third is in a different way, just by understanding the process. Okay. You do not need to memorize the equation. You do not need to think about the convolution. Just think about the process in practical way. Okay. So if you have any confusion during the lecture, please raise your hand. And be careful on this example. For the same example, the impulse response is given. What is actually impulse response? For input, if you have for delta n, the output is hn. That is the impulse response. So fortunately or unfortunately, for the given problem, the input at the 0th location is 1. Input at the 0th location is 1. For that one, what is the impulse response? What is the response? Of course, that is nothing but your impulse. Is that clear to you? X0 is equals to 1. This is nothing but your delta function. For the delta function, what is the impulse response? That is obviously Hn, and it is already given. So we can plot it like that, which is already given in our question. Is that clear to you? I'm looking for a response. Is that okay?
Yes, sir.
Okay, thank you. In the second, this is the 0th position. In the first position, let me draw it here. So here is 0th location, the amplitude is 1. At the first location, the amplitude is 2. This is 1 and this is 2. When the amplitude is 2, what should be the impulse response? Since this is a linear system, definitely the impulse response will be double. That's why I'm putting this 2. The impulse response should be 2 into Hn. Since our input is shifted with one sample, of course the impulse will be shifted for one sample. That is very practical. Try to understand this. This is your system. When the first input, that means 1, will be collapsed with your system, then you are producing what? You are producing Hn, and this is your Hn. Now, after 1 second, let's say after 1 second, the second sample will arrive to your input. So first 1 will be there, then amplitude 2 will be there. So it will definitely delayed for one sample or 1 second, let's say 1 sample. So that means the whole bunch of Hn will be shifted for 1 sample. For this case, when x1 is equals to 2, and all the amplitude, this 1 is now converted to 2, 2 converted to the 4, 1 converted to 2, and -1 converted to -2. Of course, the amplitude will be also changes. So now we can write it like this: 2 into h n minus 1. N minus 1 means it is shifted 1 sample to the right and multiplied with 2. Similarly, whenever the amplitude is 3 and the location is 2, so our impulse should be shifted 2 samples and all the amplitude should multiply with 3, and I am multiplied with those. 1 is multiplied with 3, 2 is multiplied with 3, 1 is multiplied with 3, and -1 is multiplied with 3. At for the fourth sample, the amplitude is 1, but it is shifted for 3 samples. So impulse is shifted and multiplied with 1. And you got actually the same impulse, just shifted for 3 samples. Now, what should be the resultant value? If you consider that, what should be the resultant value? Let me. Yeah. The resultant value, if you can consider this, the resultant value that at the location of -1, you need to add all the samples at the location of -1. If you add all the samples at the location of -1, what would be the result? The result is, from the graphical representation, I found the result is equals to 1. So y -1 is equals to 1. At the location of 0, y0, what should be the result? There's a 2 plus 2 plus 0 and 0. So that is 4. What should be the value of y1? 1 plus 4 plus 3 plus 0. And that is 8. What should be the value of y2? Y2 is -1, 2, then 6, then +1. So -1 plus 1, so it is also 8. In this way, you can add all those values and you can plot it to your final output. And we have found that at the y-1, what should be the value? Y plus y0, y1, y2, y3, y4, and y5. And we have plotted here. And if you compare it with your previous example or the answer, where we are taking the equation and plot it like that, we got the same result. The second one is from the conceptual point of view, and the previous one is from the equation point of view. If I want to illustrate this concept more clearly, we can have this virtual example. Let's say that I have the impulse response of this. How to get the impulse response in very practical format? Let's say you are designing a filter. So this is your filter. Any sort of discrete system is a filter. Okay, so you can memorize this. Any sort of discrete system is a filter, or any sort of even analog system is a filter, sort of a filter. So by putting this impulse, what is the output? That is called the impulse response, and let's say this is your impulse. Now, if I multiply your impulse with 3, of course, your impulse response will be multiplied with 3. If you multiplied your impulse and delayed for one sample, your impulse response will also follow the same, since this is a, what kind of system is this? What kind of system?
LTI.
Sorry?
LTI system.
LTI system.
LTI system, because if this is a linear system, then multiplication can be done. If this is a time invariant system, then shifting operation can be also done. So there is no problem. So I believe that you understood that we can write it like this, since this is a linear time invariant system. Now, keep this figure in your mind. If I have my input looks like this, if this first sample, that means 0th sample, will interact with your impulse, that is at this moment, of course, the output looks like this. If you do not have these two inputs, of course, the output will be looks like this only. And it can be represented like 1 into Hn. Now, after 1 second, that means after one pulse, the second sample will hit your impulse. That means by this time, you definitely elapse some moment. So it will start from this location, at the location of 1. That means our impulse will be shifted for one sample. And then this value 2 will be collapsed or interact with it impulse. So of course, the height, all the heights of the impulses should be doubled, comparing with the basic impulse. Whenever the third sample will interact with your impulse, what will happen? It will be delayed for 2 samples, of course, and all the height will be half, because the value is 0.5. So now the thing is, if you only have this sample and you do not have these two, In that case, you have only this output. On the other hand, if you don't have these two, only these, you have this output. Similarly, if you only have this and you do not have these tools, then you have this output individually. Now, if you have all three samples, what you need to do, you need to sum up all those together. And if you want to sum up all those together, that means you need to sum this line. So if you want to sum this line, that means you have only this impact. If you want to sum the second one, then you have this one and this one. If you want to sum other one, then you have the impact from the three inputs. You have impact from this and you have impact for this. So if you want to draw the final output, if you want to draw the final output, you want to add all those numbers accordingly. There's 2, there's 3, there's 4, and there's 5 for the 5 sample. So if I start with the 5th one, this result. For the 4th one, they'll be added this one and this one. Okay, whatever the value, you can draw like that. For the 3rd one, definitely it will be very high. For the 2nd one, yes, it will be very high value. For the 1st one, you have conventionally a little bit higher. For the 0th one, you might have that. So the result could be looks like this. And this is the final output of, so by doing the convolution sum. I'm not here to just to give you only the equation, okay, and follow this. You need to understand it graphically. Now, if I ask you a very simple question, let's say xn looks like this, a sinusoidal. Okay, let me draw it like this. So you know that this actually sampled from a sine signal like this. And if you have your Hn is a signal like this, a delta function, that is 1. So input is an arbitrary input where the input is a sine signal, and Hn is a impulse response. Fortunately or unfortunately, it is equals to a delta function or like 1. What could be the output? What could be the response of it? You do not need to give this answer at this moment. I prefer that please try to find it, okay, with the same process, with the graphical representation. In the previous class, I have given one task. Probably you have already tried it, but you can start that example. Before that, doing that example, you can start with this. So take your impulse response as a delta function. This is your impulse response. And after that, you have an arbitrary input like a sine signal. Then do the convolution of these two and try to find what is the output by the graphical representation. After that, you need to discuss or describe why the output looks like that. Okay, why the output looks like that, how you can justify your output. Okay. Okay. So at this moment, if you have any comments or any question. So if I illustrate this example a little bit more, you have this system. which is given the impulse response. First one will hit, and then you got this output. Second, this 2 will hit, you got this output. Now 0.5 will hit and you got this output. In a particular time or in a particular moment, you need to actually add all those together to get the overall output. And practically this actually been happening. This is very logical representation of the convolution, or you can say the response, how to find the response of the system. Okay, the properties of convolution and the interconnection of LTI system, they are very dynamic in a sense. For the LTI system, you can swap the multiplications, you can swap the addition and multiplication as well. So we have already proven these two terms. Okay, they are equal. You can do the convolution with xn to hn or hn to xn, both are the same. So from the block diagram, it can be represented like this. I have already shown you the commutative law. This is the commutative law. You can justify that. The associative law can be also justified with some example. With some simple example, you can justify this. Okay, take an xn with two samples, hn, h1n with two samples, or even single sample, and h2n with two or single sample. You can justify this. So you can multiply it with another a system, a convolution with a system, and then convolve with another system. Can be equal to the convolution with two system first and then convolve with your input. So if you have multiple system, if you have multiple systems, then you can do the convolution between these two and you can make your equivalent system here. So convolution 1, system 2, you make the convolution where tau is equals to tau 1 convolution of tau 2. So you can make your equivalent system here, and then you are putting your input and you get your final output. You do not need to analyze the two system now and then. You can make an equivalent system for the convolution. Please go to the example. There's a distributive law also been valid for this convolution. So those are the properties of the convolution. I believe that this is enough for today's class. So thank you very much for your presence and participation. Thank you.